Let's look at our first example. It says the National AIDS Behavioral Surveys found that in a sample of 2,673 adult heterosexuals that 170 had had more than one partner within the past year. So when in our goal here, we could try to study the actual distribution of our population. And again, basically we would refer to this as our sample proportion, p hat. And p hat, as you know, as it always is just basically what is the data that we obtain in our sample, the number of successes, whatever that means, divided by the total sample size. So usually this number of successes, you know, again, it's kind of like what does success mean, but it's just whatever we're trying to focus on. So here we'd say that those 170 people are the successes, like they're the people that said yes or no. Again, it's sort of like a yes or no question. It's whoever fits into one bracket. But in this case, that would be 170 successes divided by the total number, which were 2,673 in our total population. And again, basically, this is just a ratio or a fraction of the, you know, basically the percent of the population that fits the particular category, which again, this is always what it is. And often we like to round it as a decimal to figure, okay, what is this value as a decimal? So if we go ahead and do that, we'd have 170 divided by 2,673. This is actually the second time I'm recording this video because I forgot to hit record apparently the last time I did it. So try to maintain my level of enthusiasm even though I literally said all this 5 minutes ago. Anyways, and yeah, we can get an approximation to the sample proportion. Of course, we could write that as a fraction as well. That's about 6.36% of the population. And again, what that kind of means is, you know, roughly 6% have had multiple partners within the past year. And again, in the goal here is to say, well, what does this data say about the actual population? Because in our sample, we got 6%, but what the real population could be more, could be less. We don't really know. So we'd like to determine, well, with a certain level of confidence, what does this data say about the actual population based on the sample size and so forth. And again, it starts with the standard deviation, or again, in this case, the standard error. Since we don't know the actual proportion of the population P, we do know P hat, and we can calculate the standard error based on the sample proportion, which is, you know, again, the formula from before, P hat times 1 minus P hat divided by N, which is just sort of like saying the variance divided by N, adjusted for dealing with proportions, which is why the formula is a little different. And if we plug this in, again, you would want to plug this in as a decimal here. You could actually even plug it in as a fraction, which is a little bit more exact, but just for the sake of trying to recognize the numbers and having to do a little less writing, we'll just use the approximation of 0.0636. And as I said before, the number on the inside of the parentheses, 1 minus the proportion, is just the reverse percentage. So that would be the percent of people that did not have more than one sexual partner, or, you know, you could call it the inverse percentage, but that would be what, 93.64% or 0.9364. Of course, you could just use a calculator, and this would all be divided by the sample size, which was, we had, you know, a total of 2,673 people that we surveyed. And basically this will give us our standard error, which is basically the standard deviation for this proportional distribution. And it will tell us like how spread apart is our data. Smaller means is packed together tighter. You know, everything about the standard deviation conceptually remains the same. So we can even do this with a calculator by using second answer, because that would be the thing I just calculated. So we have the answer times 1 minus the answer on our numerator, and that's all going to be divided by the sample size. And this gives us a standard error of approximately 0.00472. And we're going to need that to calculate confidence intervals and to do significance testing, because that's the key component of the distribution. So next up is, well, what's the formula for a confidence interval? And going back to our, original study of confidence intervals, again, it's the same math as it has been every time. There's just minor adjustments for the new concepts. But if we revisit our first intro into confidence intervals when it was with respect to the mean, let's just copy that formula down from chapter 16. But the basic idea of a confidence interval is if we have a sample mean, it gives us an unbiased estimator to the actual mean of the population. Now, the margin of error is controlled by the critical value, which is kind of like how accurate do we want to be based on percentage confidence interval, and it's multiplied by the standard deviation or the standard error. And notice that that's exactly what this formula says. Basically, the basis of our population proportion P is we start with P hat. And remember, P hat is just like the sample, just like X bar for a different idea. Plus or minus the Z-score based on our desired confidence level times the standard deviation, which is, again, just that big old thing. So pretty much the same concept. I don't think we need to get into that any further. So let's say we wanted to calculate a 98% confidence interval for P. Again, we could just start with the formula. So we'd have P hat plus or minus Z star times the standard error, which we already found, so I don't need to write all that out again. And P hat is approximately, so I'll go ahead and use my approximate equal symbol since we're doing a little bit of rounding here, but 0.0636 plus or minus. And another thing is we need to find Z star. And remember, well, this is exactly the same as from chapter 16 and 17 because this is from a normal distribution from table A, or again, you could use table C also. And we don't need to worry about T star and degree of freedom and all that stuff. And for a 98% confidence interval, we could just look up a T table. And we could see, well, we want to look for a 98% confidence interval and for the respective Z star score, which in this case looks to be 2.326. And then that would be multiplied by the standard error, which we calculated in step B. Oops. And then if we run through this math, 0.0636 plus 2.326 times 0.00472. This would give us an upper end of our confidence interval of approximately 0.0746. And then the lower end of our confidence interval would be minus instead. And that should be 0.0526. And again, what this does is we're trying to approximate, well, we don't know what the actual population's proportion is, but we can use our sample as a basis. And the fact that the standard deviation gives us some degree of accuracy. Now, our conclusion, again, just like it was in the past few chapters, same exact idea, is it says, we are 98% confident that the percent of all the adult heterosexuals in the population who have multiple partners is in this range. Again, because our data showed this much, but that's not exactly right. So we're 98% confident we'll be in here. And of course, we could become more confident by expanding the interval or less confident by tightening it down. But in this case, we're pretty darn certain that somewhere between 5.3%, and I'll just answer it as a percent because it's a little bit, how data is usually displayed. But we're almost certain that the actual percentage of our, population is somewhere between 5.5% and 7.5% who have multiple partners.